In this video, I want to look at a variation of logistic growth, and this is called logistic growth with a threshold. Now, the idea here is, from the point of view of modeling populations, there's situations where if the population is too low, then there's not enough interactions between the individuals in order to have a birth rate that's high enough. If your males and females aren't getting together to produce enough new individuals, then your population will decrease. And then, of course, as it's decreasing, then you're even less likely to get things together. And so there's this sort of minimum threshold in some population dynamics where if you're above it, then you have enough interaction and your population will grow. But if you're below it, then the population will decline. Okay? And so that's what we want to model here. And building on what we've done before, just your basic exponential growth, the differential equation was the rate of change in y is proportional to y, which gave us this exponential y equals c e to the rt. We then looked at logistic growth, where y prime is the same r times y, but then times this 1 minus y over m, where m was the carrying capacity. And we saw that we ended up with a function that looks like this. That t should be in the exponent with the r there. Good, that looks better. So where was I? Yes, the change that we're going to make now is we're going to add in another factor here to change the dynamics. Okay, so before we had this much. Now I'm going to introduce a 1 minus y over t, where t is the threshold value. And then I'm going to throw a minus sign in here, because essentially what I want is I want from between the threshold value to the maximum carrying capacity, I want it to behave like it did before. And that was an upside down parabola, right? This was an upside down parabola. So when I throw this extra factor in here, with the minus in front of the y, this now becomes a cubic with, if I didn't have this minus out in the front, then I'd have a cubic that would be opening upward because the y cubed would be positive. So essentially you can say I'm throwing in this factor of 1 minus y over t, or maybe, and the minus sign, or maybe what I'm doing is I'm throwing in the factor of y over t minus 1. Right. Either way, this is going to create another equilibrium value of y equals t, because if y equals t, then this factor becomes a 0, and so now I have 3 equilibrium values. I have 0, I have t, and I have m. Okay. So looking at the graph of y prime versus y, that's this thing now. So there's an equilibrium value here of 0, and so what I'm doing here, the graph that I plotted, I had t equals 2, and m equals 10, and I have r equals 1. So just drawing that graph to show you an example. What can I see here? Well, what I see is that between 2 and 10, the slopes are all positive. These y prime values are positive, which means I'm headed uphill. But between 0 and 2, y prime is negative. So in that case, I'm headed downhill. So here's the slope field and some sample solution curves. Notice that y equals 0, y equals 2, y equals 10 are all equilibrium values, stable equilibrium at 0 and at 10, but unstable at 2. Right? That is, if the population is below 2 here, the trajectory then is that the population will peter off and go to 0. If the population is above 2, then the population will grow and look like that logistic growth. Now, it's not exactly the same as the logistic growth, because the shape of the curve on the bottom here, see, I see a bigger bend here on the bottom and a rather sharp bend on the top. That's just the nature of this isn't symmetric between 2 and 10. This peak is pushed over here closer to the 10 than it is to the 2. So that's a little bit different. Okay? But this is the notion of the threshold. And I want to point out that we talked about social distancing trying to lower R, But really the goal of social distancing is to produce a threshold at a higher level than your current infected population, right? I was talking to my brother just yesterday. He lives in the southwestern corner of Colorado. And he says their county had 13 cases. 2 of them unfortunately died, but the other 11 survived and recovered. And for the last couple of weeks, they have had no cases of coronavirus. It came in. Apparently, the threshold was high enough that it didn't get a chance to spread, or they did a good enough job of social distancing that it didn't get a chance to spread. So this is the ultimate goal of what social distancing should do. Can you make it so that the interactions between the people are so few and far between that the virus dies out, that the virus can't survive long enough before it infects the next person, right? And the population of infected people goes down. That's what we're after. Anyway, the differential equations are all here. The notion of how to solve them. I didn't actually show how I did this to get my solution curves here, but it's just another integration by partial fraction decomposition. It's got 3 factors in it instead of 2. It's not that hard to do. Solving for y then becomes hard to do, but I didn't solve for y. I just solved for t and plotted it t as a function of y rather than y as a function of t. So anyway, there's a couple of problems in your homework that are related to logistic growth with a threshold.